Hello, welcome back. We have first of all derived the one-dimensional heat equation. Now let us solve one-dimensional heat equation by using method of separation of variables. As we did in the one-dimensional wave equation, we can assume that the solution is of the form u of xt is equal to x of x into t of t, where x is only function of x and t is only function of t. That is u of xt equal to capital Xt. Okay. From this we can find dou u by dou t is equal to xt dash. Dou u by dou x is equal to x dash t. Dou square u by dou x square is equal to x double dash t. So we can substitute this in the one-dimensional heat equation. We get x t dash is equal to c square into x double dash t. Okay, so we can take variables in one side. So what we get is, or we can either divide throughout by xt. We get t dash by t is equal to c square into x double dash by x. We can take c square this side, so this happens x double dash divided by x is equal to t dash by c square t. Suppose that this is equal to some constant k. Okay, then we get two equations, that is x double dash by x is equal to k and t dash by c square t is equal to some constant k. Okay, so from this x double dash minus kx is equal to 0. From this a t dash minus c square k t is equal to 0. Okay, so we need to solve these two. Instead of this we can write d square x divided by d x minus k into x is equal to 0. Instead of this equation, t d t divided by d small t minus c square k t is equal to 0. You can convert this into our auxiliary equation, m square minus k equal to 0. This can be directly solved by using integration. Okay, so we get two. Now we have two equations. One is this and second equation is this one. Now as in the wave equation case, we take different cases for k, that is k can be positive, k can be negative, k can be negative and k equal to 0. So we have to take these three cases. Suppose that first of all we are taking k is positive. Okay, k is positive, then the equation becomes k equal to p square. K is positive, then the equation becomes d square x divided by dx minus p square x is equal to 0. That means m square minus p square equal to 0. M is equal to m square equal to p square, or m is equal to plus or minus p. Okay, so what we get is x is equal to c1 e raised to px plus c2 e raised to minus px. Okay, similarly for the case k equal to p square, k equal to p square, we solve this. That is dt by d small t minus c square p square t equal to 0. Okay, so we can arrange this in another way. Dt by d small t is equal to c square p square t. Okay, or in other words, dt by t is equal to c square p square d small t. Upon integrating, what we get is log capital T is equal to c square p square t plus some constant log c1 or c2. We can write c2. Okay, so upon taking antilog or taking exponential, we get t is equal to c2 e raised to c square p square t. So ultimately what we get is, for k equal to p square, k is positive, we get u of xt is equal to capital XT is equal to c1 e raised to px plus c2 e raised to minus px into, we can write this c3. Okay, c3 e raised to c square p square t. Doesn't matter what this alphabet is because this is arbitrary constant, so we already used c1 and c2, so we are representing that by c3. So finally, for the case k is positive, that is k equal to p square, we get solution as this. Now let us take the second case, that is, let us take the other case, that is k equal to minus p square, that is k is negative, k equal to minus p square. So we had this equation, so instead of p square we had to put minus p square here. Okay, that is d square x by dx plus p square x is equal to 0. Similarly, on the other side we get dt by d small t plus c square p square, okay, c square p square t is equal to 0. Okay, from this we can take the auxiliary equation m square plus p square equal to 0, m square equal to p square minus p square, so m is equal to plus or minus pi. Here you can take in the similar fashion, so I will solve first of all the x part. Okay, so for this we get x is equal to c1 cos px plus c2 sin px. Here, as in the previous case, we have dt by t is equal to minus c square p square d small t. So upon integrating, we get log t is equal to minus c square p square t plus again log c3. Okay, therefore t is equal to c3 e raised to minus c square p square t. So our solution for case k equal to minus p square, we have u of xt is equal to capital XT is equal to c1 cos px plus c2 sin px into c3 e raised to minus c square p square t. Okay, this is the case for k equal to p square. Next we take k equal to 0. This is a simple solution, that means d square x by d small x is equal to 0, or in the other, on the case of t, d t by d small t equal to 0. Okay, this can be solved by indirect integration. So we get x is equal to c1 plus c2x. Okay, here t is equal to c3. Therefore, u of xt is equal to c1 plus c2x into c3 for the case k equal to 0. So we have received solution for three cases, that is for case k equal to p square we have got solution u of xt is equal to c1 e raised to px plus c2 e raised to minus px into c3 e raised to c square p square t. Okay, for case k equal to minus p square we get u of xt is equal to c1 cos px plus c2 sin px into c3 e raised to minus c square p square t. Or in case of k equal to 0 we get u of xt is equal to c1 plus c2x into c3. Also, as we did the case of wave equation, only this solution matches the physical condition, that is physical experiment. So we take this solution as our solution for one-dimensional heat equation, that is u of xt is equal to, this is the winner, c1 cos px plus c2 sin px into c3 e raised to minus c square p square t. Okay. Also we can multiply this c3 inside. So what you get is u of xt is equal to c1 c3 cos px plus c2 c3 sin px into e raised to minus c square p square t. So we call this c1 c3 as c1 new c1 and c2 c3 as new c2. So since these are arbitrary constants, so we can have this. So finally u of xt is equal to c1 cos px plus c2 sin px into e raised to minus c square p square t. This is we actually take as solution of one-dimensional heat equation. So for solving problems we use this particular solution. So this is a general case. From this we have to use the initial condition to obtain values for c1 and c2, then only we can get the exact precise solution for wave equation for the initial conditions applied for the problem. Now let us try to solve this problem. So determine the solution of one-dimensional heat equation where boundary conditions are given u of 0 t equal to 0 and u of lt equal to 0 with initial condition u of x0 equal to f of x. So we use method of separation of variable, and for k equal to minus p square, that is the complex case, we get the solution which is very similar to experimental conditions. So we have arrived that u of xt is equal to c1 cos px plus c2 sin px into e raised to minus c square p square t is the solution. Okay, so from this we apply first initial boundary condition u of 0 t equal to 0, that implies u of 0 t, we apply this in the solution in this particular expression. So we get as in the wave equation case, we get c1 plus 0 into e raised to minus c square p square t equal to 0. But e raised to c square p square t e raised to 0, even e raised to 0 is not equal to 0. E raised to 0 is actually 1. So we expect that c1 equal to 0. c1 equal to 0. Okay. Now we substitute that in the previous equation, equation number 1. We substitute this, so we get u of xt is equal to c2 sine px into e raised to minus c square p square t equal to, okay, we can put this equation number 2. So we update the equation by applying c1 equal to 0. Now we can apply the second boundary condition, that is u of lt equal to 0. That is 0 equal to, we put wherever you find x, we put l, c2 sine pl into e raised to minus c square p square t. Here also only possibility is c2 cannot be 0. If c2 is 0, we get trivial solution, that means all the expression will become 0. Therefore, as in the wave equation case, sin pl equal to 0, pl equal to n pi, p equal to n pi by l. So we substitute in equation number 2 and we rewrite the equation u of xt is equal to c2 sine, instead of p we put n pi by lx into e raised to minus c square p square t. Okay, so this is our new solution. Instead of c2 I put bn, so what we get is u of xt is equal to, since c2 is arbitrary constant, we put bn sine n pi by l x into e raised to minus c square p square t. So here we apply the principle of superposition, that is we are expecting different cases of n, we are getting different solutions, therefore the linear combination is again a solution. Therefore we can say that sigma bn into sine n pi by lx into e raised to minus c square p square t is a solution. Now we apply the first boundary condition which was given in the particular problem, u of x0 equal to f of x. So we put that u of x0 equal to f of x. So we have this equation number 4. So we put t equal to 0 in equation number 4. Then we get f of x is equal to sigma bn into, okay, bn into sine n pi by lx into e raised to 0. Okay, this is 1. E raised to 0 is 1. So what we get is, this is equal to sigma bn into sine n pi by lx. That is, we get f of x is equal to sigma bn into sine n pi by lx. Okay, by using Fourier half range formula, we can see that bn is equal to 2 by l into integral 0 to l f of x into sine n pi by lx dx. So this is our formula. Okay, therefore we have from equation number 4 we have u of xt is equal to, actually we have find v of xt in this step. In order to find bn, we apply the initial condition f of x, then you find bn. So for writing the equation, you have to write, first of all, this is the equation and bn is found by this particular step. So our u of xt is equal to sigma bn into sine n pi by lx okay, into e raised to minus c square p square t. Okay, this is the equation number 4. Okay, where bn is equal to 2 by L into integral 0 to L f of x into sine n pi by Lx dx. So this is the final solution for this case. Okay, final solution for this case for the one dimensional heat equation. Okay,